In this video, we'll cover the differentiation of inverse tangent functions and explore the method to find the solution to the given problem in just a single line. Stay tuned to learn how to efficiently solve these problems using a concise approach. This is the formula we'll be using today. The inverse function of tangent is commonly denoted as arctangent, and we'll be using the symbol shown on the screen. When we differentiate the inverse tangent box, the derivative of the box becomes the numerator, and 1 plus box squared takes its place in the denominator. If you substitute x into the box, it becomes 1 over 1 plus x squared. Before solving the example, let's derive this formula first. Here we have y equals inverse tangent x, and we'll prove how dy over dx is derived. Since y is currently expressed as the inverse function, let's replace x and y to find the original function. Removing the inverse function notation and exchanging x and y gives us x equals tangent y. Now we'll differentiate both sides of the equation with respect to x. The left-hand side becomes dx over dx, and the right-hand side becomes d tangent y over dx. The differentiation of the left-hand side is 1, and for the right-hand side, we need to differentiate tangent y with respect to x. To quickly differentiate without using the chain rule, let's use the tangent function differentiation formula explained in another video. For more information, please check the link in the top right corner. We'll fill in the left and the right white boxes with y as shown in the problem, and in the right green box prime, we'll insert the derivative of the box. What term do we get when we differentiate y with respect to x? That's right, it becomes dy over dx. Therefore, we'll fill the green box prime with the dy over dx. Summarizing and rewriting, we have 1 equals secant squared y times dy over dx. Rearranging to isolate dy over dx, we get dy over dx equals 1 over secant squared y. Since secant y is the reciprocal of cosine y, the expression simplifies to dy over dx equals cosine squared y. Using the equation tangent y equals x and representing the right side as x over 1, let's draw a right triangle and label the angle on the left side as y. Since tangent y is x over 1, we can observe that the opposite side is x and the adjacent side is 1. Applying the Pythagorean theorem, we can find the hypotenuse, which is square root 1 plus x squared. By examining the triangle, we can determine that cosine y is equal to adjacent over hypotenuse, which simplifies to 1 over square root 1 plus x squared. Since dy over dx was previously found to be cosine squared y, substituting cosine y with a 1 over square root 1 plus x squared yields dy over dx is 1 over 1 plus x squared. Great! We have just derived the differentiation formula for the inverse of the tangent function. Now let's solve some examples together to further enhance our understanding. Let's work on our first example, which involves finding dy over dx for inverse tangent 2x cubed plus 4x. To do this, we'll use the formula we derived earlier. Now that the formula is ready, let's compare with the problem and determine what to substitute into the box. It is quite clear. We put 2x cubed plus 4x into the white box. Similarly, we'll put the same term, 2x cubed plus 4x, into the right to white box. And for the numerators box prime, we'll fill it with derivative of the box, which is 6x squared plus 4. Simplifying, we have dy over dx is 6x squared plus 4 all over 1 plus 2x cubed plus 4x squared. And we've quickly found the answer. Let's summarize. When differentiating inverse tangent box, we get box prime over 1 plus box squared. And conversely, when integrating box prime over 1 plus box squared with respect to x, the result is inverse tangent box plus c. Differentiation and integration are inverse processes, and you can easily see the relationship between them. So if you encounter a similar integration problem with a sin x in the denominator's box, and the numerators box prime containing derivative of sin x, which is cosine x, you can confidently write the answer as inverse tangent of sin x plus c. I keep mentioning integration while explaining differentiation because if you have a good understanding of the shape of differentiation, you'll be able to solve integration problems very easily later on. In the second example, let's find the derivative of y equals x squared times inverse tangent of 5x. Since we have two functions multiplied together, we need to use the product rule for differentiation. The derivative of uv is given by u prime v plus uv prime. So dy by dx becomes x squared prime times inverse tangent of 5x plus x squared times inverse tangent of 5x prime. The derivative of x squared is 2x. And so the first term becomes 2x times inverse tangent of 5x. For the second term, we'll use the formula provided in the upper right corner to differentiate inverse tangent of 5x. Now let's determine what to substitute into the box. Can you see it? We can put 5x into the box. Similarly, we put 5x into the right box, and for the numerator's green box prime, we fill it with derivative of the 5x, which is 5. Now that we've finished differentiating inverse tangent of 5x, we can substitute the result above and simplify further. The final result is 2x inverse tangent of 5x plus 5x squared over 1 plus 5x squared. Let's write it in a more simplified form. 2x times inverse tangent of 5x plus 5x squared over 1 plus 25x squared. The final example for today is inverse tangent of 3x squared to the power 4. Can you see the exponent 4 in the problem? As I always emphasize, when dealing with a differentiation problem involving an exponent, we need to apply the formula shown on the screen to differentiate the outermost exponent first. It is similar to the power rule you are familiar with, but you might notice the difference with the presence of the green box prime at the end. You can refer to the linked resource in the upper right corner for more detailed explanation and examples related to this formula. Let's proceed by putting inverse tangent 3x squared, as shown in the previous line, into the left box. Instead of using the variable n, we'll input the value 4 corresponding to the exponent in the problem. Similarly, we put 4 in the right n and use 4 minus 1 for the exponent n minus 1. We also fill the right white box with the inverse tangent of 3x squared, just like the left one, and we place the derivative of the box in the adjacent green box prime. To differentiate the inverse tangent of 3x squared, we'll use the formula from the upper right corner once again. We put 3x squared in both left and right boxes, and for the derivative of 3x squared, which is 6x, we place it in the numerator's box prime. Now, by substituting the derived result of inverse tangent of 3x squared into the green box prime, we obtain the final answer. Hence, dy by dx becomes 4 inverse tangent of 3x squared to the power of 3 times 6x over 1 plus 9x to the power of 4. And when simplified as a single fraction, the answer is 24x times inverse tangent 3x squared to the power of 3 over 1 plus 9x to the power of 4. I'm curious if today's video has been helpful to all of you. If you have any feedback or questions about the video, please feel free to ask. Based on your feedback, I will continue to strengthen the areas that need improvement. Also, subscribing and liking the video greatly support the creation process. Thank you to all of you who has been watching. This has been your Math Guardian, Alex.